Good evening. Myself, Dr. VIjaya Pawar, Associate Professor, Bharati Vidyapit's College of Engineering for Women. Today, we are seeing about Introduction to Fast Fourier Transform Algorithms. Discrete Fourier Transform. DFT provides uniformly spaced samples of the discrete time Fourier transform DT-FFT. DFT definition: x of k is equal to summation over n equal to 0 to n minus 1 x of n e raised to minus j 2 pi nk upon n for k equal to 0 to n minus 1, where n are number of points in the sequence, small n is discrete time sample at that instant, small k is discrete frequency sample at that instant. Inverse discrete Fourier transform IDFT. IDFT definition: x of n equal to 1 upon n summation over n equal to 0 to n minus 1 x of k e raised to j 2 pi nk upon n for n equal to 0 to n minus 1. This requires n square complex multiplies and n into n minus 1 complex additions. Faster computation: by using the symmetry and periodicity property of the complex exponential, let Wn equal to e raised to minus j 2p upon n. As we know, symmetry property is Wn raised to k in bracket n minus n equal to Wn raised to minus kn. That is equal to Wn raised to kn complex conjugate, and periodicity property is Wn raised to kn is equal to Wn raised to k in bracket n plus n equal to Wn raised to in bracket k plus n outside the bracket small n. That is, two length n by 2 DFTs take less computation time than one length n DFT. That is, 2 in bracket n by 2 raised to 2 is less than n square. Thus, the algorithm which employs computational savings are collectively called fast Fourier transforms. There are two types of fast Fourier transform. Out of that, in today's session, we are seeing FFT, first type, that is the decimation in time algorithm. As we know, DFT can be defined as x of k is equal to summation over n equal to 0 to n minus 1 x of n into Wn raised to nk. If we are splitting this x of n sequence in even and odd part of samples, then we'll get summation over n even samples x of n Wn raised to nk plus summation over n odd samples x of n into Wn raised to nk. If we are considering the even sample sequence as 2r and odd sample sequence as 2r plus 1, then we can write x of k equal to summation over r equal to 0 to n by 2 minus 1 x of 2r into Wn raised to 2 raised to rk plus Wn raised to k summation over r equal to 0 to n by 2 minus 1 x of 2r plus 1 Wn raised to 2 raised to rk. That is, summation over r equal to 0 to n by 2 minus 1 x of 2r into w n by 2 raised to rk plus Wn raised to k summation over r equal to 0 to n by 2 minus 1 x of 2r plus 1 w n by 2 raised to rk. In decimation in time algorithm, we can write the result of first decomposition as sum of two n by 2 length DFTs. That is x of k equal to g of k plus wn raised to k h of k, where g of k is n by 2 DFT of even samples and h of k is DFT of n by 2 DFT of odd samples. Then we'll repeat the decomposition of n by 2 to n by 4. So we can write this as 8-point sequence in which x of 0, x of 2, x of 4, x of 6 are the first 4 even samples and x of 1, x of 3, x of 5, x of 7 are first 4 odd samples. So finally we will get the output which is starting from x of 0, then x of 1, x of 2 onwards up to x of 7. The butterfly structure. Crossfeed of g of k and h of k in flow diagram is called a butterfly due to its shape. So we are having the structure which is just like a butterfly. This is g of k and this is h of k. So finally we will get the shape like butterfly. If we are considering 8-point DIT-FFT diagram, then we are having the point x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3, x of 7. And finally, after 3 decompositions, we will get x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6 and x of 7. Thus, in today's session, we have seen decimation in time FFT, coefficient that is twiddle factors, and we have also seen about how to reduce the computational complexity by using FFTs. For this, these are the references. Thank you.